Good evening, all. My name is Prannoy Suraneni. I'm an assistant professor at the University of Miami. Thank you very much for having me here and present on processing and reactivity of supplementary cementitious materials. A short overview of this talk. I will cover three topics primarily. First, I'll explain about reactivity testing itself and the various options you have for reactivity testing. Then I'll go into a little bit of detail and talk about reactivity and reaction kinetics. And finally, I'll cover a little bit about how you can process supplementary cementitious materials, the various options you have available. So a very quick introduction of supplementary cementitious materials. Most of you, I believe, are aware of what SCMs or supplementary cementitious materials are. These are finely ground calcium aluminosilicate materials. These replace a good portion of cement and concrete in most locations and in most concretes. Examples include fly ash, slag, metakaolin, silica fume. These are commonly byproducts of waste from various industrial processes, but they don't have to be. Some of these are, for example, the metakaolin are naturally available materials and not waste products. Why do we use supplementary cementitious materials in concrete? So primarily, there are three reasons. Arguably, right now, the most important reason, at least in North America, is that they reduce the CO2 impact of concrete, or in other words, they make concrete more sustainable. SCMs also improve fresh properties. They improve laterite strength, and they improve concrete durability as well. It is also possible that SCMs reduce the overall cost of concrete. This was certainly true some time ago, but it's not necessarily true these days. One of the most important issues the concrete industry in North America and in many other locations is facing right now is that we are kind of running out of conventional SCMs. So the most commonly used SCMs are fly ash, blast furnace slag, and silica fume. These are available in amounts much lower than cement, and these amounts are reducing. This is because of changing industrialization trends. For example, the shutdown of coal-fired power plants that is happening in many locations around the globe. So if we don't have good quality SCMs, this means we can't have sustainable and durable concrete. And this is a major issue. To ensure sustainable and durable concrete, we need to have novel supplementary cementitious materials. We need to characterize them, and ultimately we need to use them in concrete. Now, there are two important things here. One, if we want to look for global solutions, then these materials have to be available in large volumes. So if you look at this sort of availability or volume chart, you can really see that limestone, fillers, tailings, calcined clay, natural pozzolans, fly ashes are probably really the only options available. The rest of the materials are not available in enough volumes to make a huge difference. With that being said, local availability and consistency is also critical because in most cases, it is more sustainable to just use an SCM that is close by to you, even if it's not available in other places. So both the global availability and the local availability, and of course, consistency are things that must be considered. Now, the big question is, how do we identify supplementary cementitious materials? And what is this reaction or reactivity that we are talking about? Well, it turns out that most of the benefit that supplementary cementitious materials are providing to concrete happens because of their reactions. That is, these supplementary cementitious materials undergo over the long term reactions either with the pore solution or with the calcium hydroxide to form beneficial products. This reaction can primarily be of two types. One is known as pozzolanic and the other is the hydraulic reaction. So SCMs can be pozzolanic or latent hydraulic. Pozzolanic SCMs react with calcium hydroxide and water. This reaction typically needs high pH, and they form calcium silicate hydrate or CSH. In very simplistic terms, CSH is great for concrete, calcium hydroxide not so much. So these SCMs are very useful. Latent hydraulic SCMs, on the other hand, these do not need calcium hydroxide. they can react with calcium hydroxide, but they also don't need it. They react with water once activated to form CSH or calcium silicate hydrate. So these two should be separated out from materials which are called inert fillers. So inert fillers do not directly react with water or calcium hydroxide. Limestone is a great example. And it's interesting because limestone actually shows some other reactions. The extent of reaction is really quite small, but typically the consumption of water or calcium hydroxide by material like limestone is quite small. So the term inert fillers can always be a bit confusing because there is a small amount of reaction, but it's not the same as a pozzolanic or latent hydraulic reaction. Most of the reactivity tests that we'll be talking about do not really pick up on this limestone reaction. Why do we want to differentiate pozzolanic, latent hydraulic, and inert materials? Well, in the simplest of terms, these materials have very, very different effects on concrete. So pozzolanic materials, for example, this is a pozzolanic material in this case. We are showing ASR expansion. Pozzolanic materials have huge ability to mitigate ASR. Slag, which is a latent hydraulic material, not all that much. And limestone, which is inert, really doesn't do anything. There is a lot of other data as well, which essentially shows that pozzolanic, latent hydraulic, and inert materials offer very different benefits to durability. It's also the same case for strength. And ultimately, because of this, you use these materials at different replacement levels, right? So if you have a new material and you don't know much about it, reactivity testing is a fantastic step to say, hey, this material is going to help your durability or not really, or hey, you can use this material at this sort of replacement level in concrete. So that's why we want to screen out these different types of supplementary cementitious materials from inert materials, because reactivity testing is the simplest test that you can do that will give you a lot of information about these SCMs and how they will affect concrete. So then the question is how to screen or measure reactivity. Can we simply use chemistry? Can we use the bulk oxide content of the supplementary cementitious material? Really, we cannot, because if you look at quartz versus silica fume, both have roughly the same composition, which is SiO2. However, the quartz is inert, the silica fume is extremely reactive. And this is because it's not the bulk chemistry which is reacting, it's really the amorphous phases in most SCMs that are reactive. So you need to determine amorphous content, and that's unfortunately challenging. It requires the use of quantitative X-ray diffraction. So typically this is not done, especially not in standards or specifications. Speaking of standards or specifications, the US ASTM C618 uses the strength activity index test. Essentially, this test says replace a material by 25% of, replace a cement, by 25% of SCM. If the strength loss is 20% or less, it's a supplementary cementitious material. Obviously, if you think about it, this doesn't work because essentially it's a do no harm test, but if the material is doing nothing, it would still pass the test. And that's exactly what happens. Most inert fillers do pass this test because the age of testing, the replacement level, and the test limits are too low. So we have shown this, and many others have shown this as well, that the value of the strength activity index is essentially the same for inert or reactive materials. What if you measure calcium hydroxide consumption? This is a very important measurement to make, but they're not accurate for latent hydraulic supplementary cementitious materials. So for a slag, for example, it does not have to react with calcium hydroxide, so this might not be the best test there is. But still, measurement of calcium hydroxide is important, as I'll talk about a little while later. There are two tests which have gained quite some attention recently. One is the modified lime strength test, and the second is bulk resistivity. Essentially, the modified lime strength test is mixing SCM with lime and with a pore solution and measuring strength. And the bulk resistivity is measurement of bulk electrical resistivity on mortars cast with various compositions. Both of these are great. They can distinguish reactive and inert fillers. They're not able to really distinguish pozzolanic and latent hydraulic SEMs, but that is not always required. I won't cover the modified lime strength test, but I'll cover the bulk resistivity just a little bit now. Okay, so if we look at bulk resistivity, essentially it's taking a mortar cube and saying how resistant is it to the flow of electrical current. This is a test that is a little indirect because it is influenced not just by changes in the pore structure, but it's also influenced by changes in the pore solution, because of course you're measuring the overall bulk electrical resistivity. You're not separating out the effect of the pore solution. So it is, of course, an indirect measure of reactivity. But a lot of evidence from us and others have shown that this test shows promise in differentiating SEMs and inert fillers. The results inevitably show that inert fillers reduce the resistivity, whereas supplementary cementitious materials increase it. This difference is also extremely obvious or apparent as you increase replacement level, as you increase temperature, and as you increase the age of testing. So as an example here, we show a bunch of data. The limestone is the only one which reduces the bulk resistivity. All other materials increase it. And here we compare pumice, slag, and silica fume. The pumice, the slag, the silica fume all increase the resistivity as a function of replacement. On the other hand, the limestone reduces the resistivity as a function of replacement. So these results show that the bulk resistivity is highly sensitive to the reactivity. It's also known from a lot of work in literature that the bulk resistivity is a very good durability measure in terms of chloride penetration. So we thought, can we use the bulk resistivity instead of the strength activity index test? So I won't go into too much detail here, and you can check out the papers if you're interested. We developed what we call the bulk resistivity index test. So what the bulk resistivity index test does is you take cement, you make a mortar out of it, you replace 50% of the cement with a fly ash, and then you cure these at a high temperature. So the high temperature we chose was 50 Celsius. And then at various ages, you take out and you measure the strength and the resistivity. What we see is, and essentially this is done like the strength activity index test with minor modifications. So it could be made into a standard or a specification pretty easily. So before we said that the strength activity index test is unable to differentiate reactive and inert materials. These are the two inert materials. These are the three reactive materials. So you can see that if you use this approach instead of the standard approach, you get a differentiation of about 30% or 25% between the unreactive materials and the reactive materials. On the other hand, if you take a look at the resistivity, this is really quite something where the resistivity of the inert materials are below 100%, and of the reactive materials are 500 to 3000% the value of the control. So you can very easily and obviously distinguish reactive and inert materials using the bulk resistivity index test. And essentially, reactivity is accelerated significantly at higher temperatures for fly ashes and other materials. And the resistivity is sensitive to reactivity, whereas the strength is not. It's affected by a lot of other values. So it's that sensitivity to temperature that we are leveraging here. So we're working on this test. We're trying to make it into a standard or into a specification item at some point. So as I mentioned to you, this is not necessarily the major focus of the talk I want to give because it is still an indirect test. So I wanted to talk more about direct reactivity testing. So if we think of, if we take a look back at what these tests are, SEMs are reacting with calcium hydroxide or with water at high pH to form CSH. So what is reactivity, or what is an inert versus a reactive material? Well, if an adequate amount of reaction occurs, then the material is an SEM, else it's not. Now, the $1 million question is, what is this adequate amount, or what is this threshold? Obviously, whatever we choose has to be a little random, because basically you can imagine that if you take a inert material and you start adding minute amounts of reactive material, the reactivity is going to continuously increase, or the degree of reaction is going to continuously increase, not in a discrete manner. So whatever value you choose here, it has to be a little random because you're trying to pick thresholds in a continuous process. So a schematic looks something like this. You have an SCM, you have calcium hydroxide, you have an alkaline solution, and various reactions, not just one reaction, but various reactions are happening. The SCM is going to dissolve. It's going to react with calcium hydroxide. So the calcium hydroxide is consumed. Heat is going to be released in this reaction. The SCM will bind some water in the reaction, and the resultant product will have some strength and some bulk resistivity. So all of these are different measures of reaction, and you can measure all of them. Clearly, some are more sensitive than the others, as we highlighted in our discussion between the bulk resistivity and the strength. Now, you can vary mixture proportions, you can vary the solution composition, you can vary temperature, you can vary pH, you can put cement or sand into the system as well. Before we talked about systems with cement and sand, going forward, we'll talk about model systems which do not have cement or sand. So there are a lot of tests which look at various aspects of the reaction. More recently, the R3 test was developed by Professor Karen Scrivener and Professor Ruben Snellings. So we'll talk a little bit about the R3 test, but I'll primarily focus on the variant that we developed, which is the modified R3 test. But I highlighted a whole bunch of different tests here, which measure really a lot of different parameters, and they're done on model systems, cement paste, mortars, etc. And the papers are also here. If you need any papers, just let me know. Ideally, these tests differentiate inert, pozzolanic, and latent hydraulic SCMs. They give you some estimate of strength and durability, and they're rapid, robust, reliable, cheap, and simple. No one test is going to do all of these things, but of course, by using different tests, you can achieve all of these requirements. The R3 test essentially says to take calcium hydroxide, SCM, in a pore solution with carbonates, with sulfates, and to test isothermal calorimetry or bound water at 40 Celsius. We made some changes here, primarily because we wanted to accelerate the reaction a little bit more, and we wanted to simplify the system as well. So that's the modified R3 test. In this test, which I'll talk about for the rest of this presentation, we take calcium hydroxide and supplementary cementitious material in a 3:1 ratio. The liquid is half a molar of potassium hydroxide, which is a simplified pore solution. The liquid to solid ratio is 0.9. We run isothermal calorimetry at 50 Celsius for 10 days. And then at the end of 10 days, we run a thermogravimetric analysis to determine the calcium hydroxide consumption. So this looks something like this. And at the end of 10 days, once we have both the heat release from the isothermal calorimeter and the calcium hydroxide consumption from the TGA, we classify materials by plotting the heat release on the y-axis and the calcium hydroxide consumption on the x-axis. Now the question is, do we need to measure both heat release and calcium hydroxide consumption? I'll argue now that the answer is yes, but later on I'll tell you that it doesn't have to be yes. So for the first part, which is the yes, you can compare a slag, which is here, versus a quartz, which is here. They have roughly the same calcium hydroxide consumption, but they have incredibly different values of heat release. Likewise, you can compare the slag with a calcined clay. Now, they have similar values of heat release, but they have extremely different values of calcium hydroxide consumption. So the implications are clear. That is, to properly classify supplementary cementitious materials, to distinguish between inert, pozzolanic, and latent hydraulic materials, you need both. You need the calcium hydroxide consumption, and the cumulative heat release, because of course then you have XY, which is distinct on these XY plots. And as we discussed, these differences are very important for concrete durability. Now, I'll go over some results. We have tested well over 200 SEMs now, probably more than most people in the world. And these include a lot of very strange SEMs. We've tested material from Korea, China, India, Brazil, Cuba, a lot of other places. So what we see is as we go from the origin, away from the origin, the reactivity is increasing. And as we go from the right to the left, we move from pozzolanic to latent hydraulic behavior. Because in the first case, as we move from the origin, both heat release and calcium hydroxide consumption increase. As we go from right to left, at a constant value of heat release, the calcium hydroxide consumption reduces. So we can differentiate inert, pozzolanic, and latent hydraulic SCMs. So there's a boundary for inert, there's pozzolanic less and pozzolanic more reactive, and latent hydraulic SCMs. So the boundaries clearly are subjective. As I mentioned, this is a continuous value. We're just trying to put discrete boundaries on it. So clearly the boundaries are a little subjective. Now, we proposed these boundaries and I'm giving the values here so you can use them if you want to classify some supplementary cementitious materials. But essentially, really the most important boundary is the boundary of inert, and we say that it's around 120 joule per gram of heat release. So any material that's below this just does not have adequate reactivity. So typically quartz, limestone, fillers, most of these materials fall under this boundary. We have proposed slightly different values in different papers. Obviously, there is going to be a little bit of a range here. Most of the fly ashes, etc., fall somewhere here. Slags are here. Natural pozzolans are here as well. In the very reactive materials, we really see calcined clays, which can be incredibly reactive, and silica fumes as well. Now, I argued before that you need to measure both heat release and calcium hydroxide consumption, but this is not quite true. So as an example, we have seen that the calcium hydroxide consumption is correlated with the calcium oxide content. In this particular case, we show that there's a linear relationship, but in other papers, we found that the relationship is not linear. It's a different relationship. So generally, the calcium hydroxide consumption reduces as the calcium oxide content increases. And this is because for the high calcium oxide content materials, you have latent hydraulic materials. Latent hydraulic materials do not have, like the slag, for example, high calcium hydroxide consumptions. So you can use this relationship, but you have to remember that it's really not the total calcium oxide content that matters. It's a little bit more the amorphous calcium oxide content. So this is an approximation. What we can also do is when we plotted the heat release versus the calcium hydroxide consumption, we classified materials based on their composition. High calcium content has a very different slope. High alumina content has a different slope, as does high silica content. So if you have a good idea of the chemical composition, you can determine if your material is high calcium, high alumina, or high silica. And then you can use the slope of these different curves, which clearly are different. And if you have one parameter, as an example, the heat release, you can estimate the other parameter, which is the calcium hydroxide consumption, or vice versa. Obviously, you can see the scatter here in these plots. It's pretty evident. So this is going to be an estimate at best. But if your objective is simply to differentiate reactive and non-reactive materials, this is more than enough. You really don't need to measure two properties. If you want to get a very exact number, then of course you need to measure. But you want to be careful because really the amorphous content or the amorphous structure is key here. Now, one thing that's important and a lot of people forget, unfortunately, is reaction kinetics. So all the results I showed are at 10 days, and I talked about heat release, right? But the path, or rather the rate of heat release, is also important. And this is a comparison between a class C fly ash and a class F fly ash. You can see that they both ultimately reach the same level of heat, but the class C fly ash reacts much faster. And this is indicative of real life as well, where the class C fly ash reaches strengths much faster than the class F fly ash, but later age, the properties are broadly similar. So what we plotted is for a lot of materials, we plotted the 10-day heat release and the 3-day heat release. And there's a great linear relationship. The value is about 1.2 times at 10 days that it is at 3 days, except for slowly reacting siliceous SEMs. For these slowly reacting siliceous SEMs, the slope is much gentler. The reaction is much more sustained and continuous. So you don't quite get the same behavior. The idea from this is that really, in most cases, especially if your materials are reacting faster, you can reduce the test duration to 3 days, which again cuts down on experimental effort and cost. However, caution is needed with class F fly ashes and other slowly reacting supplementary cementitious materials. Now, this is especially true if the testing is at 40 Celsius. So this slide has a lot of materials, and I'm going a little over time, so I'm going to cover it quickly. But essentially what this shows is that if you run the R3 test at 40 versus the modified R3 test at 50 Celsius, in the R3 test, you don't see much reaction from the class F fly ashes. They show low rate of heat release. The class C fly ashes show much higher heat release. In the modified R3, which is run at 50, the differences between these SEMs are not so obvious at 10 days, while they are obvious in the initial age of testing. So what is happening is essentially that for the low calcium and alumina materials, which is, for example, class F and silica fume, the temperature is much more important. So the initial heat in the modified R3, where the temperature is higher. But on the other hand, when you have high calcium and alumina materials, for example, class C fly ashes or the slags, you get a lot of additional reactions because of the sulfates and carbonates. And the heat release in the R3 test is actually greater than that of the modified R3 test. So the two tests give slightly different results. Okay, so that you want to take into account when you're comparing both of the tests. But also, it looks like for the slowly reacting materials, the R3 test may not quite be enough, because clearly you can see that they're still reacting very slowly here. So this difference is again obvious when we compare the ultimate value. So the class F fly ash, the value in the modified R3 test is way higher, but it's the reverse in the R3 test because of additional reactions happening in the class C fly ash. So actually, again, the kinetics should not be forgotten. You see what is known as a crossover behavior between the two tests. So the heat actually is always initially higher in the modified R3 test. This is because of the higher temperature. But if you run these tests for long enough, the heat is mostly a kinetic effect. But in the R3 test, you have additional material, which is giving you additional reactions. So later on, at some point, the R3 test will always overtake the modified R3 test. This point of time really depends on the calcium plus alumina content, because these additional reactions are largely with calcium and alumina phases, not silicate phases. So we showed here at least that the crossover time seems to reduce in a linear manner with the calcium oxide plus Al2O3 content. Obviously, for materials with very low values, the crossover time is going to be so high that you can't detect it using a calorimetric test. So regardless, both tests work just fine. But if you're using one versus the other, it's really important to understand the nuances of each of these tests. Now, the problem is that both of these tests are really expensive. That is, they cost $50,000 each. So we want to cut down on the price. Can we get the same information that we are getting from this really expensive test using a much cheaper test? We showed that this is indeed possible. That is, if you take a mixture, a modified R3 mixture, and put it in a furnace, and you measure the bound water between 100 and 350 Celsius, you get a very close relationship with the bound water and the heat release. We have shown this, others have shown this as well. And then you can add a next step to measure the calcium hydroxide consumption between 350 and 500 Celsius. This is, of course, a rough estimation. The calcium hydroxide consumption is not going to be at a fixed range, but we show here that the bound water by the furnace and the bound water by the TGA correlate pretty nicely. Same with the calcium hydroxide consumption by the furnace and the TGA. Unfortunately, this does increase your scatter, this does increase your variability, so no such thing as a free lunch, but definitely the feasibility of the cheap reactivity test has been established. So in principle, you can run the test only for 3 days, and you can run this cheap variant where you can just measure bound water and the calcium hydroxide consumption. So this is definitely promising for standards and specifications, but of course, a lot of robustness and round-robin testing is needed. I want to move on to the second part of my talk, which is going to be processing and thermal activation. So essentially, we mentioned that there's a lot of mine tailings and other inert materials, basalt, granite, sandstone, fines, for example. There's billions of tons of these material available worldwide. And unfortunately, they're completely crystalline and do not really show much reactivity. We've tested a lot of such materials, and they really are not reactive. In the simplest terms, if you heat them beyond 1200 Celsius, that is, if you put a lot of energy into them and then you cool them down, these materials melt. And when they reform, they form an amorphous structure. So melting and subsequent amorphization is one way to activate or thermally activate inert materials. This is seen very clearly if you take a look at the basalt, which is these basalt fines are completely crystalline. Beyond about 1200, you can see clear amorphous hump, okay? And the crystalline peaks completely vanish, which is showing evidence of full melting. This is the FTIR data. It actually shows the same thing where these peaks that are seen in the inert or pre-processed materials completely merge and broaden in the amorphized materials. And this broadening and merging is a classic signal of amorphization. What does this do to the reactivity? Well, we show that beyond 1200 Celsius, when you heat these materials, there is clear activation. As an example, you go from 40 joule per gram of heat release to about 200 joule per gram of heat release. These are measured using the modified R3 test as always. However, they are at 3 days, not at 10 days. So if you want to convert to 10 days, you can use a conversion of about 1.2. The effect of composition, residence time, and temperature were somewhat secondary. They didn't have such huge impacts. But regardless, in all cases, we saw that if you take materials like this and you basically melt them and reform them, you can activate them. The resulting reactivity was about 70 to 80%, as much as fly ashes. Now, this was just preliminary testing. A lot of details are unknown. For example, we have some evidence that these materials were ground pretty coarsely. What happens if you ground them more? What happens if you change your cooling from air to water quenching? Various other process optimization details. For example, the use of fluxers to reduce temperature, flash calcination. All of these have not been explored. We are working on them. But the reactivity testing is nice because it allows you to very rapidly say, is my thermal activation process working or not? Now, the next activation process that I want to talk about is mechanochemical activation. So mechanochemical activation is essentially using high energy grinding. This is not your standard ball mill. It's actually almost considered to be a dual axis ball mill where material is rotating like, in over 2 axes. So a planetary ball mill is a great example of what high energy grinding is. And essentially using a planetary ball mill, you get increased fineness. That's obvious. And you also get some surface amorphization. Well, how do we confirm that? If you look at the XRD, you can very clearly see that the initial basalt has a lot of peaks. As you grind it, a lot of the peaks vanish or they are reduced quite significantly. A little bit of an amorphous hump is evident as well. So this is very different from the thermal activation where all peaks vanished and the amorphous hump was obvious. Here, clearly we are not getting the bulk of the material to change. We are just changing surface level. The FTIR also shows the same thing where you take your original material, compare it to the processed or ground material, and you get a broadening of the peaks in the FTIR. So we're still trying to understand these mechanisms. They're a little bit more complex than the thermal case because a lot of the changes are both localized and heterogeneous. If you look at the reactivity, you can see pretty clearly that if you grind for less than 30 minutes, you really don't do much. The grinding arguably has to be at least 30 minutes or ideally 60 minutes to pass your reactivity threshold, which is somewhere around here. And the same thing, if you grind at less than 400 RPM, you're really not doing much. We did not test 300 RPM here, but 100 and 200 RPM clearly don't work. So the results are highly nonlinear. As you can see, maybe we fit some kind of a logarithm or a bilinear curve here. But regardless, 400 RPM at 30 minutes or 60 minutes seems to be adequate to pass the reactivity threshold. Again, here we are looking at a lot of process optimization with respect to mixing with other SCMs, clays, for example, using grinding gates and other optimized grinding energy processes. We also found a lot of evidence of agglomerization, which suggests that we are generating a lot of really coarse material, which is not doing anything. So that's something that we're working on fixing as well. Now, speaking of fineness, fineness is actually really important because the finer the material, the more reactive it is. That part is clear. However, there can be a lot of different reactivity fineness relationships. These are quite complex and they depend on amorphous content, grinding method, and how the fineness is actually varied as well. So what happens here, as one example, is we size fractionated fly ashes, and we see that there is no compositional change for the class F fly ashes. It's an example here, but the class C fly ashes show a significant compositional change. In fact, just by size fractionation, you can change a class C fly ash to a class F fly ash. So obviously this has a massive effect on the reactivity. And the other thing is it also depends on the type of fly ash. So in two fly ashes here, you see that the size fractionation that is comparing below 45 and above 45 and below 20 micron induces huge changes in reactivity. But in this fly ash, it does absolutely nothing. And the reason for that is this particular fly ash has a lot of very porous particles. So the relationship between fineness and surface area for this fly ash is completely different from that of the others. So we've explored fineness and reactivity relationships a lot. And essentially what we see is that there isn't a single relationship. They depend on the nature of the starting material. They depend on how you change the fineness, etc. As an example, limestone, the change in fineness doesn't do anything to directly measure reactivity. For these two materials, which are a pumice and a glass powder, as you change from about 10 to 120 microns, the reactivity goes from 300 to about 100. On the other hand, for some of these mined tailings, which are put through a different grinding process, as you go from about 6 or 8 microns, which is very fine, to 3 microns, the reactivity changes from 40 to 150. Obviously, you can't put these two on the same curve. So the point is there are a lot of different reactivity fineness relationships, and you can kind of tune them, to play around with them to get ideal materials where the energy to put grinding is minimized, or ideal levels of reactivity where you don't have to do any more than that to get desired properties. Grinding is also possible in other conditions. For example, you can grind while being exposed to CO2, and this gives rise to, of course, another different class of materials. The final thing I want to talk about is calcium aluminosilicate glasses. So these are materials that are pure phase systems. So we take calcium, SiO2, Al2O3, mix them together and melt them and form, after cooling, amorphous materials. So we have actual calcium aluminosilicate glasses that we made in the lab, similar to silica fume or slag, etc. So a lot of folks in literature have tried to say that reactivity can be explained by just essentially one parameter. Uh, and what we show here is that this is not possible, because if you take a look at these curves, it's very clear that, for example, this gray one shows very slow and sustained behavior. On the other hand, this one shows a much faster initial reactivity, but then it kind of completely stops. This one, for example, shows a fast reactivity, but that is also sustained. Essentially, what this means is that no one parameter can explain this, because you need something for the initial rate, and then you need something for the final rate. So at least two parameters are likely required, which has kind of not been acknowledged in the literature. So a lot more work is being done on these model systems. But if you take a look, this is the high siliceous material, and this is the material which is very low in silica. It has high calcium and alumina. And really, both of them don't work quite as well. That is, if you want to get a high level of reactivity, you kind of need some amount of calcium for the initial boost, but then you also need a good amount of silica to continue the reaction. So this is something that we're working on towards the generation of synthetic or designer SEMs. Now, one thing that you may or may not have noticed from the previous curve is that all of these materials, whatever synthetic glasses we did, all of them are kind of below 500. And this does seem to be a glassy limit for most conventional SEMs, except for extremely fine nanomaterial type silica fumes. On the other hand, if you get a clay which is more than 50% kaolinite or a metakaolin, the reactivity is huge. Metakaolin, for example, has reactivity more than 800 joule per gram of SEM. So why is this difference? What are the metakaolins doing? Is it just the question of the significant surface area, or is it something else? Again, a topic that we are working on to understand why clays are so reactive so that this can be exploited. Maybe we can transform other SEMs into clays, or we can look at blending in clever ways to get the most out of limited resources. So with that, I want to conclude my talk. We have shown the development of the modified R3 test, which can be used to differentiate inert materials, pozzolanic SEMs, and latent hydraulic SEMs. You use it to measure reactivity, and you can use it to screen out these different types of materials. Ideally, you measure both the heat release and the calcium hydroxide consumption, but this is not necessarily required, because one can be used to estimate the other if you use the chemical composition in a smart way. The modified R3 test duration can be cut to 3 days, and it can be performed using a furnace, but you want to be cautious for slowly reacting siliceous materials, because 3 days is not enough for them. The furnace material, the method, I'm sorry, does increase variability, so that's another thing you want to be cautious about. Reaction kinetics are absolutely critical. Do not ignore them. Thermal and mechanochemical activation is feasible. We are studying the mechanisms, working on optimization, and there's a huge amount of tunability that is possible with fineness and processing that must be exploited. Finally, I talked for a little while about the calcium aluminosilicate glasses. These offer a lot of insights into reactivity of conventional and novel supplementary cementitious materials. These are fantastic model systems, but our results seem to show that one structural parameter does not or cannot explain reactivity. Thank you very much for your attention. I appreciate it. These are our sponsors who we are grateful for. And I'd also like to thank my team, especially Ying Wang and Shivakumar Ramanathan, who did a lot of the work that we talked about. Thank you.